The recording has started. So the example goes as, in this example, we show how to find the location of a person's center of gravity. So suppose your lab partner has a height or L of 173 centimeters and a weight of 715 newtons. You can determine the position of his center of gravity by having him stretch on a uniform board supported at one end by a scale as shown in figure 8.12, which is that figure on the far right. If the board's weight is 49 newtons and the scale reading, so that scale reading, the one on the foot end, and the scale reading F is 350 newtons. Find the distance of your lab partner's center of gravity from the left end of the bed. So from the left end, so that last part from the left end of the bed, or of the board, it's very important because then it's giving us something that we must use as our what we must use as our point of axis rotation. Okay, so what you quickly do, like we did yesterday, is draw a free body diagram. Okay, so for this lab partner, draw you want to draw a free body diagram. So how you want to, okay, let's just do that. So how we want to do this is, so we do that. So how you want to do this is, so you're going to say, uh so this lab partner is like that, then there is this, then he's lying, but we were just going to use forces so that we don't overcrowd, because remember this is a free body diagram, so it should just have forces. So what then this is telling us is, this person is lying here, and this here, the fact that this on this end, okay, on the left end, this thing that is there, that's where the head of this lab partner is. So the fact that his head is not going down, it's because there is a normal force here. Okay, that's why his head is not going down now. So there is a normal force that is there, so take note of that. Then what else do we know is that midpoint of this board, that's where the weight of the board is going to be felt. Okay, at the midpoint of this board, that's where the weight of this board is going to be felt, so that's the force there. And then for the uh for the weight of this person, remember what's the center of gravity? Center of gravity, that's where we take as as the weight of a person or of an object is going to be concentrated at. Okay, so that's your center of gravity. So meaning that even for this person, where his center of gravity is going to be, that's where his weight is going to be. So weight of a person, huh? Okay, then we now come to this. There is a scale on the foot end of the bed. Now that scale that we have on the foot end of the bed, it's, take note of it, even though it's giving us a reading, kindly take note of this, even though it's giving us a reading, but it's providing an upward force. Now why are we saying it's providing an upward force? Because if there wasn't this upward force, that this upward force is what's actually supporting the weight of this person. Because if there was not this upward force, the legs of this person would have gone where? Would have gone down. But then why is this that this scale is giving us a value? The scale is giving us a value of how heavy the person's legs are. So the fact that this person's legs are heavy, they're saying that they are heavy by what? By 350 newtons, right? If the legs, oh, if this side of the legs is heavy by 350 newtons, and there is a force that is ensuring that the legs don't fall down, it means that the force that's acting upwards to ensure that the legs don't continue going downwards, it means that it should be equal to what? It should be equal to the reading that is on the scale. I hope that makes sense, right? So, so we've now understood uh, what our free body diagram is telling us, and once you've done this, then you are done. Okay, and the question is then telling us to say our axis of rotation is what? Our axis of rotation is here. So meaning that we know that the torque for the normal is going to be what? The torque for the normal is going to be zero, isn't it? So now let's now use the condition for equilibrium. So the condition for equilibrium, we know there is this one torque. The sum of the torque is going to be zero. So we then say torque from the normal plus and for this first one, I won't take into consideration the signs because I'm just adding the talks, huh? But the second one, that's when I'll take note of the signs of the talks. Then now I've got the weight of the person. Oh, sorry, the talk of, yes, where, the axis. Yes, yes, that's the n that I've put there. You can see the n on top. Yes, yeah, that's the norm. Okay, great. Yeah. So, okay, thank you for the question. So, yeah, so then the torque from the normal, the torque from the weight of the person, then the torque from the weight of the board, then the torque from the from this force that's preventing the legs from falling down. So it's equal to zero. Now let's put signs to our torques. So for the axis of rotation that we've chosen, the torque for the normal is zero. Then what is going to be the sign for the torque for the person? For the person, is it going to be negative or positive? So it's going to be negative. Okay, great. Yeah, so it's going to be what? It's going to be negative. So negative weight. So the weight is what's providing the what? The force. Okay. Then we now then the distance or the r. That's the x component of our center of gravity. Okay, because that's the distance that this person is from this axis of rotation to here. And so that's where our center of gravity is, because when you get a person, or any object where the weight is going to be acting on, or where the weight is going to be concentrated, that's the center of gravity. So meaning that when we find that x, then we know the center of gravity of this person, huh? Of course, just the x component of the center of gravity. So that's why I've put the x there. Then for the torque for the board, it's going to be negative as well, right? So it's going to be negative weight of the board. Then the distance for this weight of the board, it's what? The weight of the board is usually going to be the half the length of the board. Okay, so that's where that is going to be. And something interesting, they are telling us that the person, when you see how the person is fitting on the board, you see that the person is fitting exactly on the board, right? So we just assume yeah, that the person's height, that's the uh, uh that's the length of the board. Okay, so we can take it like that. So meaning that where is the weight of the board going to be felt? It's going to be felt half over the half of the height of the person, or half of the length of the board. So that's going to be the length of the board half. Okay, so that's L over 2. Then what's going to be the torque for this force here that's preventing the legs from falling down? This one here, it's going to be what? It's going to be positive. So it's going to be positive, and the force is what? It's F. Then the distance is going to be the whole length of what? Of the board, which is equal to the height of the person. So we use L there. Then 0. So having done that, we are done. So what then you do is you just put things on one side, and what you do is you say, uh, okay, move this here. The reason why I'm doing it is so that it makes the work easier. So then it's going to be FL minus the weight of the board, L over 2. Then you then say over the weight of the board over the weight of the, sorry, am I saying the, sorry, the weight of the person, pardon me, the weight of the person, the weight of the person there. Then you have it. Then you just put in the values. So the force at the legs, it was what? 350 newtons. Then the distance. Now you may have noticed that in this particular equation, uh in this particular equation, they used centimeters and they were able to get the answer. But remember, to always be on the safe side, you would always want to use the SI units. But usually for these questions, what I've realized is that usually uh it's okay, like they pardon you to use centimeters. I don't know what the logic is, but usually they pardon. Okay, it's not that they pardon. It's almost as though for this particular kind of question, it's almost as though they allow that's if I can put it in that context. And the main reason is, okay, I'm not sure, but because even when you check Shomes, even them they answered these particular questions in the same way. So I don't know whether it's just some reservation on this particular question, or I don't know why. But that's something that I just thought I should bring to your attention. However, remember, you never know who may be marking your paper, so you never want to take risks. So it's best to convert. Huh? So let's convert 173 centimeters to 1 to meters. So that's going to be 1.73 meters. Then uh, for the weight of the board, it was 49 times half. That was 86.5 centimeters. So that's going to be 0.865 meters over 750 newtons, which was the weight of the person. So once you do this, you're going to get your value, which is going to be 0.78 meters. Okay, so if you want, you can say 0.9 meters. So now, since the question was given in centimeters, here you may want to convert. So converting this, it's what? It's going to be 70, just multiplied by 100. So 79 centimeters, which is going to be the x coordinate of what? Of your center of gravity. So you see, it's all about just looking at the question, analyzing it, and then you should be good to go. So that's pretty much about how you want to handle these kinds of questions. Okay, so we can proceed then. Okay, so where are we? Yeah, so now let's now look at a number of examples on this particular concept because they really love these questions. So again, the strategy, remember, draw the free body diagram. You saw when I drew the free body diagram, it was easy even for you people to start seeing the how to go about it, how to go about it. So that's usually what's important, huh? So please let's take note of that. Okay. So you draw that first diagram, then you want to apply the second condition of equilibrium, which is that your sum of torque must be your sum of torque must be equal to zero. Then the other condition of equilibrium, it's for the forces. So how you do, and the key thing for the torque is that choose your axis properly, because when you choose your axis properly, it makes your work easier, especially for those questions where they don't give you the axis, huh? Okay, then apply now for the sum of the forces. So depending on the question, you may want to break down the force component into the x horizontal and the y vertical, right? So then that's going to give you some equations there, and those equations are going to lead you on how you are going to go about. So like I always say, I don't like the approach of memorizing. So let's look at this question. So, the question is saying a 50 Newton bowling ball is held in a person's hand with a forearm horizontal, as in figure 8.13a. The biceps muscle is attached 0.03 meters from the joint. The ball is 0.350 meters from the joint. Find the upward force exerted by the biceps on the forearm or the ulna. Uh, and then, so biceps, we know it's this muscle. Anyway, when you do anatomy, you'll be able to cut bodies and then you'll be able to see them. So, and the downward force R exerted by the humerus on the forearm acting on the joint. So, neglect the weight of the forearm. So, in short, we are not going. So, in short, what they are saying is that when we are calculating our forces and when we are calculating our torque, don't consider the weight of the forearm. We know that the weight of the forearm would be concentrated at the center of gravity, but they've told us to neglect it. So that's why, remember, from the time that we started, I've always been emphasizing that read the question entirely. No matter how easy the question seems, read the question entirely. You are going to miss a lot of things when you just leave it there, because it's just telling us something interesting. Again, it says, and the slight deviation from the vertical of the biceps, ignore it. So what they're basically saying is that look at this. You look at that biceps, it's actually occurring at an angle, right? Or rather, the biceps muscle, it's attaching to the humerus. So the humerus is this bone that's between your shoulder and your elbow, huh? So you see that the biceps is acting at an angle, but they are saying neglect that angle. So you see the importance of finishing reading a question, because imagine when you start calculating angles and then you get disappointed that actually those things are not even relevant uh, in your question, or in what you are trying to what in what you are trying to calculate. So please, again, I reiterate it that always read the question from the beginning. Okay, I think having done that, I think, or rather having said that, I think we can then proceed. So that's what we are looking at. So the question is asking us to find the force that's being exerted by the biceps on the forearm. And so this force is going to be upwards, because remember, the biceps is what allows you to move your arm or your forearm, rather to move your forearm up, isn't it? That's the biceps. So meaning the direction of that force, it's going to be what? It's going to be upwards because it's what is causing that this hand does, or this forearm doesn't fall down like that. So it's providing an upward force. So that's why that force for the biceps, you see that it's a positive one going, and the reason I'm saying it's positive because it's upwards, right? So that's important to take note of. Then you see there's the other downward force exerted by the humerus on the forearm. So now you see this humerus, when it's coming to join with the forearm, it's exerting rather a certain downward force. Now, why have they specified that a downward force? Because you could actually say, wait, isn't it also helping to lift this one up? But of course, it's the muscle that is maintaining this hand or this forearm in this position. And so the humerus, it's actually in some way, it's almost as though it's actually putting on a downward what? A downward force. So those are the two forces that we are going to be calculating. So now let's now write our free body diagram. So the key thing again, don't look at how complex the diagram, the drawing looks. Just go for the physics. Once you go for the physics, you never go wrong. So let's look at it now. So again, what we do, we look at our torque. So what's our torque? So first, so let's draw our free body diagram. So they've told us that the total length of the forearm, then there is a bowling ball, and the bowling ball has got a weight of 50 newtons. So meaning the 50 newtons is acting at that point. Then this is our axis of rotation, and we are choosing it because that's where we are going to get rid of certain forces which we don't know. Like this force, the same R force, the one that's the downward force from the humerus. We don't know what it is at this point, so it's good when we make this point our axis, so that we can just cancel it. Then we now have the biceps is at this point, which is from our point of axis, the biceps is at 0.03 meters. Okay, and it's providing an upward force which is keeping this thing up. So you see, we only have how many forces? Three forces. But when you look at just the question itself, it's almost enough to depress somebody, right? So just look at it like that. So here what you do, you look at the condition for equilibrium. The sum of torque is zero. What torque do you have? So you're going to have a torque due to the R there, and I'm not designating the signs yet. I'm not designating the signs yet. Then plus, then you're also going to have the one due to the humerus. So for the humerus, let's can make it an H. Then for the bowling ball, we can make it B or BB. Anyway, but yeah, so the torque for the humerus, that, then the torque for the bowling ball, it's that. There have to be their sum has to be zero since this thing is in equilibrium. So then let's now look at now the signs. So of course we know this R, this is where our axis of rotation is, so it's zero, perfect. Now let's oh my goodness, yeah, so let's now look at our humerus. So our humerus, what torque is it going to produce? Is it going to produce a positive one? Yes, because it's going to raise the arm counterclockwise, right? So we have the force there and the distance they've given us, right? That's the one there, 0.03 meters. Okay, I don't know what that's happening. Okay, so that and that, right? Then we also have for the bowling ball now. So the bowling ball, it's going to cause a what? A clockwise torque, right? So it's going to be negative. Great. So from there now, it's just algebra. Okay, so okay, so that's that. So sorry, always put units, huh? So always put units. So it is negative 50 newtons. Then that's since it has now moved, so it's 50 newtons. Yeah, so it's going to be, so the force is going to be what? 583 newtons. So that's the upward force that's being provided by the what? By the by the biceps, sorry, by the biceps. So now, since we've got the forces, we can now find the force R. So what do we do? Since it's in equilibrium, the sum of the forces is what? Is zero. So what forces do we have? We've got these forces are acting in the what's this? They're acting in the vertical, so we can put a vertical there. Why? So we've got R, which is downwards, so it's going to be negative R. Then you've got the one for the humerus, which is positive. Anyway, let's write them properly so that we can appreciate them, that they are forces. So force R. Then you've got the upward for the humerus. Then you've got the downward for the bowling ball. Then it's equal to zero. Then since we know what these other forces are, yeah, since we know what these other forces are, so what we say is we just move this to this other side and say the force R is what? Is the bowling, sorry, is the force of the humerus minus the force of the bowling ball. So this one was 583 newtons and this is 50 newtons, and so the difference is what? 533 newtons. So you see, so the key thing, but when you look at how the question was looking before we started solving, it was looking all over the place, right? But once you separate it into its components and you just look at the forces and you look at the torque, you then realize that it's not as complex as it may look. So let's now look at one question which they really love in your tutorial sheets. I'm sure this one should be there, and it's this question. Okay, I love this question because it just brings so many concepts into play, and I think this should be in your tutorial sheet if I'm not mistaken. So a uniform ladder of 10 meters long, or rather uniform ladder 10 meters long and weighing 50 newtons rests against a frictionless vertical wall as in figure 8.14a. So you see the ladder they're talking about, the first diagram on the right. Huh? Okay, if the ladder is just on the verge of slipping, okay, when it makes a 50-degree angle with the ground, find the coefficient of static friction between the ladder and the ground. So this is a very interesting question, and many people usually tend to get lost on the concepts for this one. But how you want to look at this particular question is this. Let's begin looking at the forces that are acting on this ladder. Okay, so that we can build them together. That way you have a better understanding of it. So what you are having is uh so here's the ground, and then here is the wall, and then here is the ladder. So this ladder has made an angle of 50 degrees. Okay, though I'm just drawing this so that people can get the context, but when yeah, and I'll draw the free body diagram then later on. Then the length of this ladder is 10 meters. So then, and then we know that there is friction which is occurring. So ask yourself, what really does friction do? Friction goes against emotion. Okay, so that means that the question you have to ask yourself is, if this ladder is to slip and fall, how should the downward part go? Should it go in the direction of A, or should it go in the direction of B, the down part, if this ladder is to slip and fall? I'm hoping you are saying that if it's to slip, it has to go towards the A direction, right? That's when it will fall down. So it's that means that because for the ladder to slip and fall, it means that it has this down part has to go towards the A side, right? So this means that friction is going to be opposite that direction of motion. So what this basically means is when we have our ladder here, let's make it blue. So when we have our ladder there, it has made an angle of so this is the ground. It has made an angle of what? Of 50 degrees. But there is friction here. So it's actually the friction that's actually preventing the ladder from what? From falling. And this makes sense because if I'm sure you may have tried this. Whenever you're trying to put a ladder, you don't put it somewhere slippery and then you want to climb on it. Nobody does that, right? You always want to put it where it's a little bit rough, and then you can even climb on it even when nobody is there to support you. And the reason is that you are relying on the friction there. I hope that makes sense, right? So then, what we then do there, so we figured that one out. Then, what other thing are we going to have that we have to take note of this? Now we know that at this particular point where the ladder is, this particular point, if there is no normal force, it can continue going down the ground. So there has to be a what? A normal force. Okay? So that's about it. What next can we appreciate? The next thing we can appreciate is, where does the weight of an object occur? The weight of an object is going to be felt where? Is going to be felt at its center of gravity. And so because this is a 10-meter ladder, it's going to be midpoint here. That's why you're going to have the weight of the ladder. The weight of the ladder. There is one force that we shouldn't neglect, the last one, then we can start our calculations. The last, and please, I hope you are not memorizing, but you are understanding how these forces are coming about. Huh? Then, the other force that we want to concentrate on is this one here. The one that I'm circling there on the left. There is a particular force that is acting there. And you may be wondering what force can be there. It's the force of the wall that is acting on the ladder. There is a force that's acting from the wall that's acting on the ladder. And it's this force that's causing the ladder not to what? Not to enter into the wall. Because if there was no wall, the ladder would have continued where? Going this side. But the wall is providing a certain force opposite to the ladder. Okay? Or to make it more clearly, it's providing a force at this point. Okay? So that this ladder doesn't continue going where? Going into the wall. So meaning the next force we have to write is the force here that's coming from the what? From the wall. So we can put it maybe, what can we put it? Let's put it wall. Let's put it as W. Then this one is going to be weight of the ladder. So that's like a small L that I've put down there. So once you've done this really, the job is done. It's just now about just putting in figures, because once you've done this, there's no way you can get the question wrong. So has everyone understood how we've come up with these forces? Okay, please, in case someone says yes and you are uncertain, you've got human rights, you can just say, not so clear. And then we'll be able to uh, go through it. Since everyone is comfortable, that's really good. So then we can proceed. So, how do we go about this? Interesting. So, okay, great. So, what we are going to do then is look at the forces. Or if you want, we can look at the torque, but yeah, or maybe we can say, yeah, if we want, we can even start with the torque. But why I want us to start with the with anyway, let's start with the talk. Since for the other questions we've been starting with the talk, and when we get stuck somewhere, then we know that we have to start with the forces. So sum of the torque has to be zero because this thing is in equilibrium. Then we are going to have what forces are we having? So we've got the force of friction. We've got torque for friction. We've got torque of the normal. We've got torque of the weight of the ladder. We've got torque from the force of the wall, and they have to be zero. So to make work easier, what do we do? We make this our what? Our axis, so that we cancel out the what's this? We cancel out the torque for the friction and the torque for the normal, so that we only remain with the what? With the torque for the weight of the ladder and for the W. Now that's interesting. So then what then do we do? So what is the torque going to be for the weight of the ladder? Is it going to be negative or positive? It's going to be negative, okay? So it's going to be negative. So it's going to be negative. And what's the weight of the ladder? They've told us the weight of the ladder is 50. So the force is going to be 50. Then the distance, remember this is weight, it acts on at the center of gravity. Okay, so it's going to act at the center of gravity. Okay, isn't it? So it's going to act at the center of gravity, which is the midpoint of the ladder, which is going to be 5 meters. But then you see that this particular weight, usually weight has to come like this, right? It has to be 90 degrees to the ladder, but you see that this weight is at an angle. So then we have to put angle, because remember when you've got torque, there is the formula like this one, right? Sine theta. So we have to now put in this particular angle. What is the angle of this particular weight? Because weight normally has to be 90 degrees to the object, right? But this weight is at an angle. So we have to find out what this angle is. So what you do is, let me use black so that everyone can get this. So you'd complete like a triangle like this. So you've seen that triangle. Now you know that here it's 90 degrees, right? Where I've put, yeah, that's 90 degrees. So if there is 90 degrees there, and then there's that 50 degrees to the ground, and you know that a triangle is equal to what? 180 total. So meaning finding x, what's x? X is this angle here, the angle which I've indicated x. So meaning that x is going to be what? 40 degrees. So meaning the angle that, so the angle at which the weight is acting on the, is acting on this particular uh ladder, it's acting at an angle of 40 degrees. Before I can continue, has everyone understood why that angle is 40 degrees? Okay, it's quiet. Okay, so we put sine there, 40 degrees. Then we now go to the next talk. So before I put the sign there, so then we go to the next talk. So what's the next talk? Is it going to be positive or negative? So if this force is moving like that, it's going to move the ladder what? Anti-clockwise, sorry. And so meaning that this torque is going to be what? This torque is going to be positive. Now, do we know what the force W is? No. Do we know what the distance from the axis of rotation? Yes, it's at the end of the ladder, so it's 10 meters. Do we know what angle it's acting at? So remember your angles. There is this principle of angles that says when angles are making a Z, okay? When angles are making a Z, the angle here and the angle here are the same. I'm sure you remember those, huh? So it means that this angle, the ones where I'm shading black, the ones where I've shaded black, so those angles are the same. Perhaps you may remember this from your mathematics, grade 12. So those angles are the same. So meaning that this force W is acting at an angle of what? Sine 50 and then 0. Interesting. Don't worry, we are almost there. We are almost there. Don't get worried. So having done that, now you see that we've got two variables. We've got, yeah, is it two variables? Yeah, yeah. So you see that we've got, no, we only have one variable, right? Okay. So, okay, yeah. So we've got one variable there, which is great. So using just algebra, you just make W the subject of the formula. And then of course you're going to find your answer to be 21 newtons. So let's just save on time, but this is just algebra, just punching on the calculator and then you get your values, huh? So this is 21 newtons. So there you're going to get what? 21 newtons. So yeah, so that's that. You've got the angle, you've got that, yeah. So you've gotten that. Now remember what the question is asking us to do. The question wants us to find the coefficient of static friction. In other words, they want us to find this. Okay? Now, we now go back to our earlier diagram that we started with, where we said friction. Yes? Yes? Where? Yes, you're saying? Oh, okay, okay. That's what the formula says for torque. You see? Remember when you started the topic? Yeah. So it's just the context. It's just about the what's this. So it's all about the context of that. Okay, let me. Okay, yeah. So it's just basically about the context of that. Yeah, so that's pretty much about it. So it's just the formula, about the angle. But okay, I don't know what has happened to this. It's like I was pressing somewhere. Let me just readjust the things here. I don't know what has happened. I don't know where I was pressing. Okay, okay. Oh my goodness. Mm, okay, okay, great. Okay, okay. I think things are now back to normal. Okay, yeah. So you are saying that you didn't understand where we got the sign. Okay, so that's when we first started the topic on what's this on talk, we said whenever a talk is acting at an angle, that is sign. And the reason why that is sign, anyway, you can watch the video that we did on talk on Google Classroom. But yeah, that's just how the formula is. When you get an angle, you use the sign. But of course, you can also verify it with regards to. Anyway, you can watch the video because that was explained in more detail. Yeah, so it's just part of the formula. But when you watch the first video we did on talk, it's going to explain why it's sine because we talked about how we even derived it. Okay, so just to wrap up before time runs out. So we've been asked to find the mu and oh sorry to find the static of the coefficient of static friction. So we know that what's friction force. So friction force is what? Friction force is going to be so friction force, we say max there, is going to be coefficient of static friction times the normal. Okay, so what this means that if we are to find the coefficient of static, we have to uh, find the normal and also find what the friction is. So we have to find these things. So then what do we do now? Okay, so here now that's where we're now going to use our forces. Okay, so this is where we are going to use our forces. So you've seen we've used our torque to find that. Now let's use our forces. So we know that the forces which are acting on the ladder, we've got that friction, then you've got the weight of the ladder, then you've got the normal, then you've got this weight here, W. So what you do is that you put the forces in their components. Okay, so you put the forces where in their components. And so what you're going to do is, let's say the sum of the forces in the x component, they're going to be zero, right? So what forces are in the x component? You see that the forces that are in the x component is what? It's friction, and then there's also this W, right? So there's that W again, so it's going to be minus P. Oh, sorry, not P, W. The W that's there. So now you may be wondering why that friction uh seems to have a positive sign. Because remember, what we are looking at here, we are trying to look at the forces, and we know that okay, when something is pointing towards the right, it's going to be positive. But more so, the friction here is what's important because it's actually what's keeping this thing to be in the position that it's in. Okay, so what does this tell us? So it means that if these are the forces in the horizontal, it tells us that the friction force is equal to our W. And remember that we found our W to be what? To be 21 newtons. I hope everyone is clear on this one. So that's how we've used the forces in the x direction. So now let's now use the vertical forces. So the vertical forces, we have that. and that. So then what are the vertical forces? Vertical forces, we are having the normal, and then we are having the weight of this ladder, isn't it? And we know that what's the normal? Normal is supposed to be equal of the weight of the ladder. So weight of the ladder was what? 50 newtons. So meaning that what's our normal? Meaning our normal is what? Is 50 newtons. So now you remember this equation that I wrote here, the one which I wrote here to say, for us to find the coefficient of static, we have to say the frictional force over the normal. So we found the frictional force to be what? To be 21 newtons, and the normal to be 50 newtons. And so our answer is what? Our answer is 0.42. If you want, you can put 0, but anyway, you can just put that. That will be okay. Yeah, but so you see, so that's the key thing. Oh, sorry, this has no units. It's a coefficient. Yeah. So you've seen. So if you wanted, you could have started with the forces, or if you wanted, you could have started with the talk. So the key thing is let the question guide you. Because once you let the question to guide you, then you won't panic. You know exactly what to do at each and every point of the calculation. So that's something important to take note of. So are there any questions?